I can't hear, but I can see.
Can you hear now?
Yes, we can hear you.
Okay, cool. Yeah, so as I was saying, so one of the big missions in our team is to enable telepresence, human telepresence. And that what that means in our case is to be able to enable highly photorealistic creation of 3D humans such that humans can be digitally present in spaces that are far removed from them in a digital space. So nowadays, this dream of having telepresence be actually enabled and happening in the world is becoming more and more closer to reality. With the introduction of the Apple Vision Pro as well as the Meta's codec avatars, we're seeing a lot of photorealism and very high quality avatars being created. So differently from these existing technologies that use specialized hardware, whether that be capture systems or the light stage to capture an avatar or multi-view capture systems, and also specialized technology for display, for example, the headsets, the Apple Vision Pro or the Quest. What we are interested in doing in our team, our mission is to be able to create AI-mediated 3D telepresence. And so we want to use the power of generative AI and large generative models, to be able to create democratized telepresence technology that is accessible to anyone, to be able to create avatars, and it just works off of ordinary webcams. And also by using AI, we want to be able to create enhanced experiences than just simply lifting individuals into 3D. And create a little bit of bending of reality and change their reality slightly. And I'll come back to this and describe how we envision changing reality a little bit. And
make everything a little bit interactive. Can you actually turn on your camera from Zoom? They just told me that. Okay, great. Thank you. Sorry again for that was the last interruption.
All right. So just to give you some idea for the type of technology that we've been building at NVIDIA, this is just a short concept video that I'll play. But believe me, this will all tie back to my initial question that I had on the title: do we really need 3D? And it'll all come together. And so just bear with me. This is all sort of to lay the stage of where we're going.
Enable 3D video conferencing on any device without specialized software or hardware. Starting with a standard 2D camera sensor that's in most cell phones, laptops, and webcams, NVIDIA Aerial enables 2D video streaming to the cloud over 5G with low latency, tapping into the processing power of Grace Hopper. Maxine 3D converts these 2D videos to 3D using cloud services. This brings a new dimension to video conferencing with Maxine 3D visualization, creating an enhanced sense of depth and presence. You can dynamically adjust the camera to see every angle and motion. Engage with others more directly with enhanced eye contact. And personalize your experience with animated avatars, stylizing them in simple text font. With Maxine's language capabilities, your avatar can speak in other languages, even ones you don't know.
NVIDIA is revolutionizing communications technology with generative AI. NVIDIA 正在使用生成式 AI 来发明新的交流方式。NVIDIA 3K AI を用いてコミュニケーション技術に革命をもたらします。
NVIDIA Aerial and NVIDIA Maxine 3D together with Grace Hopper bring immersive 3D video conferencing to anyone with a mobile device, revolutionizing the way we connect, communicate, and collaborate. Welcome to the future of communications.
So I hope you were able to hear at least parts of that video, given the audio was a little soft here. But so not only have we created just this concept video, we actually created a full 3D system for interaction between two users, and we demonstrated this at SIGGRAPH last year. And so here in what we're showing is we had two light field displays manufactured by Looking Glass, and we had two users with a single camera. They were interacting in 3D, and so the way that we achieve this is that every single frame, 2D frame, is lifted into 3D, and to reconstruct the person in 3D, and then that is transmitted to the receiver and can be viewed on a 3D or a light field display. So I'm going to talk about the underlying technologies that helped to enable this, this whole pipeline of enabling democratized AI-based 3D video conferencing. And as part of that, I'm going to, try to answer this question, this philosophical question, and whether we really need 3D ground truth data as of today to be able to learn 3D, and what can we achieve without using any kind of 3D supervision, to what level and what detail can we achieve geometric information. So to walk through that and try to understand this, I'm gonna start by talking a little bit about generative models. And they first came around in 2014. But in about 5 years, when we had sort of the style GAN series of models, we started to see very high quality photorealism start to appear, especially in the quality of faces that were being synthesized by these models. And there's been independent studies that have been conducted to try to understand like how good the quality photorealism of these faces is. And they've been shown to human subjects, and basically these studies have found that they're virtually indistinguishable, at least by human observers, from synthetic faces. And also there's some studies that suggest that they can help to mitigate some of the dataset biases that may exist by being able to synthesize additional data from these models and create more balanced data sets. So let's just quickly talk about how these unconditional GAN-based generative models work. At the core of them, the basic idea is you have a random number or a latent code that you generate randomly that goes through a generator. The generator network then produces a RGB image. And you can synthesize a lot of highly photoreal random faces by passing in different random codes. And the way that these generative models are trained is as following. Basically, the generator generates a fake image, and then you also separately have this training set of real images, and you give a fake image or a synthesized real image to a discriminator network, which then tries to say whether it can recognize whether it's a fake or a real. And by making that decision, it feeds back information back to the generator to try to improve the generator, which tries to fool the discriminator. So both of them are improving simultaneously, and one trying to fool the other. So this is really great. And, there were this evolution of StyleGAN, then StyleGAN 2 and StyleGAN 3 networks, specifically from NVIDIA. And the StyleGAN 2, while it achieved very, very, very good photorealism, it sort of had this camera sticking artifacts where it didn't do quite as well when you, moved the facial image in the view. However, StyleGAN 3 introduced a lot of anti-aliasing filters that try to sort of solve these problems of avoiding these texture sticking artifacts, such that you could actually move the face around in the actual rendered image. So these were all really, really great, but none of these actually produces 3D consistent or geometric, synthesizes anything geometry. Like it's just 2D, it's pure 2D. So in 2020, we introduced EG3D, which is a 3D aware GAN or generative adversarial network. And what it was able to achieve was it was able to achieve highly photoreal synthesis of both 2D as well as 3D content. So these geometries that you're seeing for these faces are actually purely synthesized by the GAN, and they're not, they're not based on any kind of multi-view capture or depth capture, etc. So, and the very neat thing about this work is that we trained this model purely by using a large collection of 2D images captured from the wild. It was not trained using any 3D data at all for supervision, or multi-view data for that matter. And so I'm going to talk a little bit about how we achieved this, which is a step toward trying to answer this question of like, do we really need geometric information today to do any kind of geometric processing? Right, so let's look again at how we train 2D GANs. And so the basic idea of training 2D GANs, as I mentioned previously, was you have a generator, it generates a fake image by taking in a random code, and then that's passed on to the discriminator to critique. Now, when you're trying to do a 3D aware GAN, you change the formulation slightly. And now, instead of the generator actually producing a 2D image, it produces a scene representation, a 3D scene representation. And the key thing is that this scene representation should be differentiable, such that you can back propagate gradients back through it into your generator for it to be able to learn. So the particular scene representations, and I'll come back to the scene representations that we use. But then once you have that scene representation, what you can do then is you can render images from that 3D scene representation from various viewpoints, and take one of the rendered images, provide that to your discriminator, and obtain feedback about whether this is a real or a fake image. And by that feedback, they can be back propagated to the 3D representation and back to the generator to help the generator generate better fake scenes, so to say, 3D scenes. So this is kind of the process of how you would learn to create 3D scenes without actually having 3D supervision, simply from 2D supervision. So let's look a little bit closer. So contrast this as we saw this. The 2D GAN produces a 2D image, goes to the discriminator. 3D GAN has a 3D representation. You render an image, you give it to the discriminator. And like I mentioned, again, this is the real images that you use to train these GANs are simply collections of real world images. In our case, we tried real world faces. We also tried artistic faces derived from paintings, etc. A data set containing artistic faces, and then another data set of cat faces. So so what some of the advantages of this 3D aware GAN are that you don't need 3D ground truth data, which is hard to acquire and generally tends to be very little and collected in the lab. And the other thing that happens is that when you collect 3D data in lab conditions, the system trained on such data doesn't generalize well to the real world when you take it out to images in the wild. However, there is one potential problem when you're trying to train a 3D aware GAN, which is it takes a very long time to train. It's very computationally expensive to train. So the GAN itself takes around 25 million iterations to train. And then by introducing this 3D representation in the middle that requires rendering, that step is very computationally expensive, and that makes GAN training even slower. So let's see how we try to solve this problem of trying to make 3D aware GAN training faster. So the neural representation that we use in this case, or the scene representation, the 3D scene representation we use is neural radiance fields, or NeRFs, which is a very nice representation in that it's fully differentiable. You can pass gradients back through it. But there is one problem with this representation, which is that when you render using NeRFs, you essentially have a 2D image that you're trying to render, and for each pixel, you have a ray that goes out into volumetric space, and you have multiple points on the ray that you sample. So, for example, right here is a depiction of this. You have these various points on the ray that you need to inference, which essentially means the neural representation is a MLP, and you need to inference for each of these points. And typically, the number of points per array is anywhere to the order of 100, 9600 to like 200. So that's a lot of inferences that you need to do, and especially if you want to render at a high resolution, that's a lot of computation. So to solve this problem of very high computational need while training this 3D-aware GAN by introducing the NERF in the middle, the way we solve this is that we introduce this representation called a tri-plane representation. And what this does is that essentially it eliminates a large part of the neural network and instead converts it into these 3 axis aligned planes, which are aligned to the X, Y, Y, Z, and Z axes. And this tri-plane representation is sort of like a projection of the 3D information that would have been in the 3D volume onto these 3 planes. And so the way that you inference with this is that whenever you want to figure out the RGB color and opacity at a particular volumetric point in space, you find the projection of that 3D point on the 3 triplanes. You obtain the features from the 3 triplanes. You either sum them together or concatenate them, and you pass those features through a very small MLP, which is just 2 layers. So this effectively reduces your forward passes a lot, the computation required to do the forward passes significantly. And this allows us to be able to train the GAN model in turn in a fairly fast way and successfully train it in a reasonable amount of time frame. And the other thing to note is that this tri-plane representation is also nice because you can essentially stack them at the end of a generator here. So you essentially have the triplanes be the output of the generator. And so you can use these 2D convolutional type neural networks, or even, you can use transformers. There's a lot of networks out there that work with 2D content. So you can very nicely infer these triplanes from a GAN model because they're sort of planar. And CNNs are very good at sort of predicting this kind of planar information. So you predict the 3 triplanes stacked, and then you reshape them back into this axis aligned, and that's how you work with them. So these are great. However, even with the lower computation, we are able to render directly from the GAN model only at a resolution of 128 by 128 pixels. And what we're interested in finally are like much higher resolution images of size 512 by 512. So if you were to try to natively render from the GAN during GAN training at 512 by 512, that's a lot of computational cost. So what we do is we instead render out by 128 by 128. And then we have these just pure convolutional layers that learn to upsample these lower resolution images that are generated by the fake images generated by the GAN to this higher resolution. These 2D super resolution layers are cheap to implement. They're not as computationally expensive. However, if you notice carefully, they are not inherently 3D. So they result in making things slightly not multi-view consistent. So you kind of see these flickering artifacts in the beard, for example, when the viewpoint changes slightly, because they're not 3D aware. So so this was a problem that we wanted to solve, and I'll talk about next how we try to solve this. But just these are some more examples of the faces that are generated from EG3D, just like randomly synthesized faces and their texture. So this was a very, very first initial step towards trying to get geometry, and pretty reasonable geometry, out of essentially learning from 2D images where no 3D is used, which was very fascinating and surprising that we could even get to this level of detail. And just to mention that this EG3D work, even though we did it initially in the context of faces, this triplanes have been used widely in many, many different other applications in computer vision, in modeling 3D objects, as well as scenes. So, it's been one of highly cited works, and people have expanded on this and applied to many other applications. So let's go back to this texture sticking artifact that we had when we were, trying to do super resolution using 2D convolutional layers. And how do we get around this problem and how do we natively generate geometry? So the geometry that we had from this was always at a lower resolution. How can we get to even higher quality geometry beyond what we have here? So this is our new work. This is called WYSIWYG, and we're presenting this. It's accepted to CVPR this year, 2024. And what it stands for is what you see is what you GAN. And the idea here is that we want to be able to create geometry, very high resolution geometry, again, using purely generative models that are learned with just 2D collections of 2D images. And we want to be able to do this at the native resolution of whatever our image content or image information is, RGB information is. So you can see here that when we look at the depth here, we're able to resolve very high details. We're able to resolve facial hair, the texture on the cap, and also, the iris details and so on and so forth. And I'll describe briefly how we actually achieve this very high resolution, yet being able to train the GAN with a reasonable amount of training computational cost as well as memory was the goal. So so the first simplest solution that you can try to do when in order to try to increase the spatial resolution is that you can just simply render from your GAN. Instead of rendering a 128 by 128, you can start to try to render at much higher resolution, let's say 512 by 512. You can do that. It just will take, half a terabyte of VRAM to do. And you'll probably be able to fit at most one training image per GPU. And so you could scale across GPUs. That's one option. But besides the crazy compute that it takes, we also found that when you increase the spatial resolution, you actually can no longer just do with 96 samples along the depth along the ray. So if you actually, this is an example where we kept the same 96 samples, and you kind of start seeing these aliasing artifacts. So the conclusion here was that you actually have to increase the number of samples along the ray as well to be able to render natively at the high resolution. So this is terrible because this means that you need even more memory and even more compute to be able to train this GAN, right? So this is completely not desirable because the samples are just being undersampled here. So what was our solution to this? So the solution to this that we found was to come up with a way to do smart sampling. And the idea here was you don't want to just sample uniformly in 3D space all the points along the ray, but instead you want to try to figure out, if there's some way you can actually find where most of the depth information or the actual volume lies, where it's the opacity is non-zero, and dedicate your samples to that region. Now, this is something that is ordinarily also done with NeRFs. It's typically done. So you would typically there's this 2-pass sampling strategy that people do, which is they first render at a lower resolution, and then there's you dedicate rays along regions that tend to have non-zero opacity. But we wanted to do this much more aggressively, such that we could really drastically also reduce the number of samples from 96 to, let's say, 8 or 10 or 16 samples per ray. And so that if the number of samples per ray are less, we can then scale out the computation along the X and Y dimensions. So we get high resolution spatially, but then we can reduce the number of samples per ray. So that was the general idea. And so the other sort of idea to enable this smart sampling was to try to make your surface really, really thin. And so if your surface is very thin and it's, you're going to have just like a shell-like surface, and that effectively means that you don't actually have to sample a lot of points in volumetric space, right? So in order to do that, we changed our NeRF representation, which is a pure volumetric representation, a dense volumetric representation, to one based on SDF. And it had we learned like a beta parameter, which essentially says what is like the tightness or compactness of the surface that you're learning. And so with this, so this was the first thing, is like making your surface like very much shell-like and very thin. And the second important thing we used to enable the smart sampling was that we actually learned a sampler. This is we trained a sampler, which is a CNN. And so what we did here was we first generate like a volumetric probe by doing some coarse, we generate a bunch of uniform points coarsely, and then we get the opacity of those points in 3D space. And then with the rough estimate of this coarse points, we pass this into a CNN, which then predicts at a high resolution exactly where the most of the probability of the volume is in 3D space. So with this learned CNN, we're able to then dedicate samples only to the parts of the 3D volume where the CNN predicts that, yeah, there's a high likelihood that there's some non-empty space here. So these are essentially the two ideas. One is to make the volume shell-like, and the second one is to learn a sampler that tells you exactly where you should actually put your samples along the rays. And if you're interested, please come by and check out our poster. And so these are some more additional results beyond the first one, initial one that I showed, wherein you can see that these are all synthetically generated faces. We're now able to resolve a lot of details of the teeth, the eyes, facial hair, as well as textures on the clothing, eyeglasses. And this is truly fascinating because, again, like I said, this is all just learned using a collection of 2D images, right? And so if this is the kind of level of detail, geometric detail that we can get, then it really makes you wonder, like, do you really need 3D data? And what can it get you? How much can we get away with just using 2D data to learn geometry? So we're very excited about these results, and I will now, so these are sort of our sort of building blocks in generative AI models that we've been building for creating digital 3D humans. And I'm going to talk about some of the things that we've been using these foundational blocks, these generative AI models for, and what sorts of applications we've been building using them. So, so moving on, so one of the big things that we've been working on is a model called LP3D. And what that stands for is essentially a model that allows you to take a single 2D image of a person and be able to reconstruct them in 3D. So this is essentially a conditional 3D face synthesis task, wherein now you're not doing unconditional generation of random faces, but instead you're conditioning your synthesis on one provided image, one 2D image of the person, and you want to lift precisely that individual into 3D. So this is work called LP3D that we published last year at SIGGRAPH. And what you see here on the left is an input image. So this is the left, and this particular image is an input image. And on the right, you see this particular face being lifted into 3D, and then you can render it from different viewpoints once you have them in 3D or RGBD. So I'm going to talk about how this generative model that we trained previously enabled us to actually train this sparse view lifting algorithm or 3D reconstruction algorithm. And as you can see here, that it works with cat faces, and it also works with the stylized faces, and it preserves like the photorealism in the input image very well, which is key to enabling sort of photorealistic telepresence, what we believe. Okay, so here, just kind of quickly, I'm going to show you a demonstration. So what you're seeing is a video is being captured in real time with an iPhone. This is my colleague, Michael. He's one of the co-authors of this paper. And this is the input video on the very left. And this is the output. He's been lifting into 3D. And this is the 3D reconstruction of depth, or the depth that's being created. And you'll see here that he also, wears eyeglasses, and the system can continue to, work well with the sort of variations as well. Okay. So yeah, so like I briefly mentioned, our goal is you have an input image and you want to be able to reconstruct using a single image, reconstruct it in 3D. This is inherently an ill-posed problem, right? How do you solve this? So one way that, if you're using the generative models that I showed previously, one simple way that people try to solve this problem is, what you can do is that you can do something called GAN inversion. And so what GAN inversion tries to do is, given an input image, you try to learn the latent code, which is like the random code that you input into the generator. You try to learn via optimization, stepwise optimization. You try to learn the latent code, which would then produce the 3D representation. And from the 3D representation, you render images, and you want that rendered image to match your input. So that's the basic idea. And you try to optimize using an optimization algorithm that latent code that would produce this image in the given viewpoint. So this is the kind of results. This is my image, and on the right is the kind of results that it produces. It's also very slow. It takes about 2.5 minutes to optimize. That's not something that you can operate in a video conferencing or a telepresence system. So it's just not feasible. However, it can produce decent results. You can take an old image where there was obviously no 3D, and you can get depth out of that image for that individual. So what we want to do instead is we want to use this idea that we have this generator, this 3D generator, that allows us to have paired data, essentially. It allows us to have paired data of 3D as well as 2D. And we want to exploit this paired data to learn an encoder, or like a feed-forward network, that will take in a 2D image as the input and produce a triplane for it. And the nice thing is that we can use this generative model that we had previously to create a large amount of this paired data by creating a large amount of synthetic data, rendering it from the generative model. So this is, in essence, what our system does. You have a 2D input image, and you have an encoder, and the encoder encodes it into a triplane representation. And once you have the triplane, you can render it from different viewpoints. So, so our solution to trying to learn this encoder, interestingly, there's like two conflicting goals. We realized once we started learning it, is that one is, when you input an image into this encoder, it can be in different viewpoints. So the one thing you want to do with this encoder is you want to canonicalize it, which means that you want to frontalize it. You always want the triplane that it produces to be in the standard frontal pose. So there's the need to canonicalize faces. But on the other hand, when you're lifting somebody's face conditionally based on their input image, you also want to preserve their any specific like facial details, like their tattoos or any kind of shape asymmetries or things like that are specific to them. So on the one hand, you want to canonicalize, but on the other hand, you want to preserve individual details. So how does one achieve these two conflicting goals? So our solution was that we have these two VIT encoders. There's one VIT encoder that essentially learns a canonical triplane representation. And then there's another, and this is a low resolution triplane representation at 64 by 64 resolution. And then we have another encoder that actually tries to copy a lot of the texture and the detailed geometry from this 2D image and paste it back onto this canonical triplane, so that, like their hair details and so on and so forth are carried forward. So this two encoder architecture is what we found to perform quite well at preserving as well as canonicalizing. And with that, we're able to render it in different viewpoints. So in order to train the system, what we essentially did was we generated a really large data set using our previously introduced generative models like EG3D. And the data sets basically comprised of triplanes. And from the so we created a lot of random triplanes. And from the triplanes, we rendered multi-view images that we used for supervision. But one thing we realized was that when you generate data purely from these generative models, they don't encapsulate all of the variation in images that you might encounter in images in the wild. So for example, images in the wild have different focal parameters. For example, they capture with different camera focal parameters, principal points, focal lengths, etc. And also there's these pre-processed images are never perfect, and there's always some cropping differences and shifts and so on and so forth. So what we found was it was important to apply some data augmentation to this data that we synthesized using a 3D aware GANs, and specifically zooming in and zooming out, some principal point changes, as well as focal length changes when we rendered this data out of our triplanes. So this enabled us to more closely represent the kind of variations you observe in the real world, in the wild data. So the training pipeline for this methodology is as following. You use a random latent code. You generate a triplane from EG3D. You render that triplane. We render out depth, segmentation maps, as well as the raw images from different camera viewpoints. And then we take these multi-view inputs, we feed them into an encoder. The goal of the encoder is to produce the triplane back. And we have both these triplanes now we can supervise. And so from this rendered triplane, we synthesize a lot of data, the same kind of outputs, and then we supervise the two. And that's how we learned this encoder to go from a single rendered image back to the triplane or the 3D representation. And surprisingly, what we found was that even though we'd not trained it on stylized faces, for example, on the bottom row, it still worked decently well out of the box for faces such as these doll faces or stylized faces. So this was a neat, interesting application. And we also found that it could work well with videos as well. So here, we're not doing any kind of temporal smoothing or interaction between the temporal frames. We're simply applying the lifting frame by frame on individual received frames. And it seemed to maintain pretty decent temporal stability. There is some instability, and part of it comes from the fact that in this pipeline, you do have to estimate the head pose and create a normalized crop, which then goes into the encoder. And oftentimes we found that, so the facial pose estimation algorithms that give you the facial pose are typically not very, very temporally stable. And those tend to introduce some of the shake that you're sort of seeing over time. But if that can be solved further, the stability can be improved quite a bit further. And finally, we also did some more extensions of this work after publishing the original work at SIGGRAPH last year. And the two extensions we did was we found that we could actually improve the head pose as well. So what we do is the head pose tracking algorithms that we use in the normalization, they give you some head pose, but then the encoder itself predicts another slight delta on the pose as a correction that we use. So we found that we can use that encoder to correct any wrong poses. And additionally, we found that we could also use the encoder to predict a segmentation of the foreground and background at the same time by predicting like an alpha mask in addition to the RGB as well as the geometry. So these are all sort of extensions that we did beyond publishing the original work. So with these, all this fundamental technology that we built, one is to do unconditional 3D synthesis as well as conditional 3D synthesis on top of it based on images. We were able to enable this, build this entire AI-mediated 3D telepresence system that I showed previously, and which goes beyond just sort of lifting people into 3D. We can, with the system, we can, for example, we can stylize people, and we can lift their stylized images into 3D. We can also take 2D images in which we correct, for example, eye contact or their gaze direction, and then lift those into 3D. And we can also change the lighting of the scene and then lift those 2D images into 3D with lighting change. We can also kind of drive people's portraits from another driving video and then lift that portrait so you can kind of anonymize people. And also you can change sort of the audio in real time. And I showed an example of this before. So there's the idea here is that, you know, these, so this using AI to do this telepresence system sort of allows you to then tie your system with other AI technologies that kind of bend reality and enhance reality, so to say, than as we know it, in especially for the purposes of teleconference, and then for content creation and gaming and for media and so on and so forth. So I'm switching gears a little bit, and I'm going to also talk about some of, you know, there's another way that folks have been also looking at to try to generate 3D from large generative models, specifically diffusion models. And this is a work that we're also presenting this year at CVPR, which is Dream in 4D. And it is a method for unified text and image-guided 4D scene generation. And so let me briefly describe what this is all about. So this is a little bit different, but conceptually, I want to just kind of show the various flavors of how, you know, you can try to achieve 3D or even 4D synthesis using models trained purely generative models purely trained with 2D. So here the task that we wanted to try to explore was, for example, if you're, say, given a text prompt, like a panda is eating ice cream, or a dog is running, the task that we wanted to try to do is, could we use a diffusion model that is trained, you know, 2D diffusion models or video diffusion models to actually create a 4D content. By 4D, what it means is a 3D representation that also animates or moves over time. And the description of that is using this text prompt. And then the other thing we wanted to explore was you could either provide a text prompt to kind of create this 4D representation that is animated 3D representation, or in addition, you could provide a single image or a collection of images, and it should sort of obey this conditional, as I showed in the case of faces, this conditional input that you have the appearance defined by these images, besides having the text prompt that describes the actual 3D model, the 4D content that you want to generate. So I'm going to briefly just talk about the pipeline that we came up with here. So if you're familiar with the score distillation sampling loss, that is the core idea that we used in this work. And the score distillation sampling loss in the case of diffusion models, basically the idea is that the diffusion model learns a step of denoising content. So it tries to learn the 3D scene by creating. So let me back up and try to explain a little bit. So in the case of diffusion models, the idea is you have a randomly initialized 3D scene, similarly to how we had in the case of GANs. You render images from it from various different viewpoints. And then you add a little bit of noise to that rendered image. And then you pass it to a diffusion model to denoise. And then based on how the diffusion model denoises and comparing that to the noise that was actually added, you can essentially set up a loss between the two that then guides the diffusion process such that this 3D representation can be learned. So in our specific case, in order to solve this problem of trying to learn 4D animation, we broke up the problem into 2 steps. So what we found was that it's important to learn first a static 3D scene really, really well. And once your static 3D scene is learned well, then in the second step, it animates well. And we found that there was a correlation between the quality of what is learned in the first static step and how well it is animated in the dynamic second stage. So in the static stage, the other key important thing we found was that it was important to provide guidance from not just a 2D diffusion model, but also a 3D diffusion model. And by 3D diffusion model, what we mean here are models that the diffusion models that have been fine-tuned, for example, using large collections of rendered multi-view images, for example, from the Observerse data set. And what this helps to do is typically when you just try to render from 2D diffusion models, to learn 3D from 2D diffusion models, they have this sort of Janus problem or multi-face problem, where you will create a dog with multiple faces, because if you render them from different viewpoints, the rendered images look correct. They look plausible from every single viewpoint. But together as a whole, they're not multi-view consistent. So the 2D diffusion model helps to kind of overcome this sort of Janus problem. And the 3D diffusion model, however, is trained with synthetic objects. And so it tends to produce very plasticky, synthetic looking, not photoreal images or content. So the 2D diffusion model helps to overcome that. And then for the deformation stage, we use a video diffusion model specifically. And we learn a deformation field, which we encode as a hash encoding to try to model this second stage. So let me show you some results of this. And this is a very nascent emerging field. Before we published this work, there was only one other work by Meta AI Research that had published a similar work. But this year at CVPR, I do believe there's a couple of different works in this particular topic besides ours. So I encourage you to check those out as well. And so in terms of the results, let me so best take you to this website here where you can we can scroll and see. So this is the kind of results that you can obtain. And these are the geometry that you can obtain. So the prompts are indicated here. Oh, sorry. Apologies. Let me see. Maybe I need to. There we go. Sorry. So yeah, so these are the kind of results. Can you share? Sure. Right. So so these are the kind of results that you can see. And this is the geometric details, level of geometric details, appearance, and so on and so forth. So while this is early work, this is still very interesting because this is sort of, adding another dimension, because we talked about how we can learn geometry and then we can do very good geometry. And here we're sort of exploring a different dimension where, in addition to geometry, we can also learn from 2D generative models to learn to animate the 3D geometry, such that we can get free viewpoint videos, in essence, that can be viewed by a viewer from video animation from any different viewpoint. Yeah, so with that, I will go back to my slides, and